Hello, and welcome to the final part of this worksheet, graph conceptuals. So the first two problems on this worksheet were very kind of algorithmic. They were very pen and paper type problems. They're very mechanical problems, as we would say. This one, we're going to get a little bit more conceptual. That means that these problems are going to be probably deceptively difficult. So if you don't fully have the understanding to them, don't worry about them right now. In particular, I think problem 3 takes a lot of Problem 2 and 3 take a lot of real understanding of DFS and BFS, which you will get as you do the algorithm on paper more and more often. I find that the best way to build up a conceptual understanding of an algorithm is to learn it by rote, learn it mechanically, and then once you know how all the parts work, you can start asking yourself, why are the parts the way they are? Anyways, don't worry about that much. These are pretty hard problems. This is very much the kind of stuff you will see in 70. So if you're currently taking CS 70 or have taken in the past, which you most likely haven't, but if you have, because it's possible, these might give you flashbacks because these are very much the kind of things that you will get on your midterm 1. So basically, I'm going to go over how you would do some of these problems and hopefully give a little bit of insight into how some of these work. So the first thing to note here is these are all true and false problems. And so in general, true and false problems, the easiest way to go about this is these are just statements. So the easiest way to prove something is false is to come up with a counterexample. So if they give you a statement and you can say, here's an example that meets your criteria, but is not true, then it's false, right? That's the easiest way to do it. True can be a lot trickier because true, you kind of have to convince yourself. So for those problems which are true in here, we'll go through them and hopefully I can help you understand a little bit. Anyway, but let's start with the first one. So if a graph with n vertices has n-1 edges, it must be a tree, true or false. Okay, so here's what I'm going to do is I'm always going to start by, unless I can tell instantly this is true, let's say we can't tell if it's true or false instantly, I'm going to try to come up with a counterexample for a couple seconds, and if I can, then I know it's false. In this case, I actually can come up with a counterexample. Here's one. Great, here's a graph with 4 vertices with 3 edges, and it's clearly not a tree. Notice that this graph doesn't say anything about being connected, so this is not a tree. Another example would be if you had something like this, where you had 3 nodes, and then you have something like this, where you have a self-edge on one of the vertices. This graph doesn't say it has to be a simple graph, which outlaws self-edges. So this is also another example of a graph that is not a tree, even though it does have the correct number of vertices and edges as a tree. Something that is true, though, is that if this question is false. But something that is true is if you have a connected graph with n vertices, n-1 edges, then it must be a tree. So just as a challenge to you, try to connect this graph fully with 2 edges and have it not be a tree. You won't be able to do it because the only way you could do what I was doing before in those previous examples is you either come up with a cycle or you come up with a like a self-edge or something like that. And if you have a cycle or a self-edge, that means that you're missing an edge to connect an element of the tree. So you can't. That's why it's true, or that's why it's false, and that's why it would be true with another criteria. But in general, you can just say this is false, and hopefully you see we just came up with a counterexample. Okay, so moving on. Every edge is looked at exactly twice in every iteration of DFS on a connected, undirected graph. Okay, what does that mean? It basically means we're going to consider every edge and therefore every node that edge is leading to twice in our traversal of DFS. So this is one that is just, I'm going to tell you right now, it is true, and then let's explain a little bit of the logic that goes into it. So imagine you had a graph, and let's say that it looked, like this, for example, and we want to run an, I wrote, oh yeah, that's supposed to be a D. Let's say you have this, and you want to run DFS on it starting at A, right? The DFS, it doesn't really matter what order, or whether it's pre-order or post-order. But basically the idea is we're going to look at every edge. There are 3 edges here twice. And so let's run just a quick kind of like DFS pre-order maybe in our heads a little bit and see what's happening. So first thing you're going to do is you're going to start at A. So you're going to pop A, you're going to visit it. And then you're going to add both of its children. Adding both of its children, that's the step where you look at the edges, right? Because in order to look at B, to figure out that a child is B, you have to look at the edge. So I'm just going to mark the edge and say we've looked at it. And in order to look at C, you need to mark the edge, or you need to go along the edge to C. So I'm going to say we looked at it. Okay, great. So we have both B and C. Next thing we're going to do, because let's break ties alphabetically, is we're going to look at B. So we're going to visit B, and then we are going to add all of B's children that have not been visited already. Okay, what are B's children? B has a child that is A. So we're going to have to look at this vertex again to look at A. We're not going to add A to our fringe or anything. We're not going to visit it again. But hopefully this makes sense. We want to look at all the children. And just as in an undirected graph, B is a child of A is a child of B, right? And that's always the DFS traversal. We look at the thing, and then we look at its children. Moving on, let's look at C now. So we're going to visit C, and then we're going to add its children. It has A, so it's going to look at this vertex again, and then it has D. Great. Then we're going to look at D, we're going to visit it, we're going to add its children. Its only child is C. So hopefully what you can see is that we did look at every edge twice, right? We looked at it once when we were going to the child the first time, and then we looked at it again when we were the child looking back at the parent that originally added us. If you remember also when I was doing the DFS traversals in the second part of this worksheet, there were a lot of times where I said, okay, let's look at a node, and then said, oh, well, we don't have to add this node to the fringe because this node's already been visited. That's basically what's going on here. We're looking at an edge that isn't strictly necessary for us to add. This is something called the handshake principle. You will learn about it in CS 70 as well if you have not already. And basically, that's all it's saying is that you're looking at one edge and then you have to look the other way back. So this is true. This is a rather in-depth explanation of it, but I hope it makes a little bit of sense. Okay. 3, this is probably the hardest one on this worksheet. This is, this is again, when you take 70, you'll get very used to reading this very technical type of language. But basically, all we're doing is we're doing a BFS. I'll let you read it on your own. I'll just explain it in my words. We're doing a BFS. And during BFS, we're adding certain things to the fringe, which is a cube. So it's basically saying, if we were to look at the minimum distance from any node that we're looking at to the original source node, the difference between that node and any other node currently in the BFS fringe is going to be either 0 or 1. It says less than 2, but that has to be 0 or 1 because we're dealing with integers. So less than 2 implies not 2, right? So 0 or 1. And you can't be a negative distance away from the starting node, right? Like that doesn't make sense. You say, oh, this is 3 nodes away. You can't say this is -1 nodes away. That doesn't make sense. So it must be either 0 or 1, right? This language, intentionally confusing. Anyways, so let's kind of look at an example and explain this. I'm, again, just going to tell you that this one is true. And let's look a little bit why. So let's imagine that we have a graph over here. And let's just make it look like let's give it an E, and we'll give it an F, and we'll give it a vertex. That's actually not a good edge to put in here for this example. Yeah, sure. So you have a graph and it looks like this, right? And let's say we want to start our BFS traversal at A. Okay, what is the BFS traversal of this? At this point, you might even be able to do in your head. It's just what? A, B, C, H, D, F, E. Why can I do that? How did I do that in my head? This E looks ugly. How did I do that in my head? Well, I basically looked at, we're going to start at A, and then we're going to list off everything that is 1 thing away from A. Then we're going to look at everything that is 2 away from A, and then we're going to look at everything that's 3 away from A, right? And then I just alphabetically sorted it to break ties. So in other words, everything within this first band is 0 away from our starting node. Everything in this band is 1 away. Everything here is 2 away, and everything is 3 away. That is fundamentally how BFS works. That's what I meant in the previous question when I said it kind of radiates out towards the center. And I drew something similar in the previous question, if this is still confusing. Right? So that's how BFS works. Okay. So this number here also represents the minimum distance from a node to the source node, right? So if the source node is A, of course, A is 0 away from itself. C is only 1 away in the minimum, F is 2, et cetera, right? Notice we're saying minimum because if you wanted to get to, if you wanted to get to A from C, you could go C to B to A, and then you would be 2 away, but that's clearly not the minimum, right? Because you could just go directly to A from C. So that's what we need. In other words, each one of these bands, these red bands that I've drawn represents the DV of any given node. So D of C, for example, is equal to 1, right? Because it's minimum weight. Okay. So now let's actually address the question. It's basically saying that at any given time, at some point, all of these nodes are going to be in the fringe and then they're going to be popped off and then they're not going to be in the fringe anymore. So at any time that they are in the fringe, there will not be a difference of greater than 1 with any other node that is in the fringe. Okay. So you might say, well, that doesn't make sense because what if, for example, H and E are in the fringe at the same time, right? H is 1 away from A and E is 3 away from A. So 3 minus 1, of course, is 2. So that would seemingly make this false. But here's my question to you. Will H and E ever be in the fringe at the same time? And the answer is no, actually, because remember how BFS works. BFS looks at everything is 0 away, then everything is 1 away, then everything is 2 away, then everything is 3 away. Okay, which means that in order for 3 to be in the fringe at all, we must have looked at D, right? We must have looked at something that is 2 away, right? Because we're not going to add the thing that's 3 away till we look at the thing that's 2 away. There's no other way to get to it, right? But also keep in mind that in order to visit a 2, right, we're not going to add anything, we're not going to add E until we visit 2, or until we visit D. In order to visit anything that's 2 away, in order to visit D, we must have already visited and therefore popped off H from the fringe, right? Because we're not going to visit anything that's 2 away until we visit everything that's 1 away, which means that this H will never be in the fringe at the same time as this E. And there is no example where anything that is 1 away from our source node will be in the fringe at the same time that anything that's 3 away is. And again, the reasoning is just because you're not going to put anything that's 3 away into the fringe until you're visiting things that are 2 away. You're not going to visit anything that's 2 away until you've looked at everything that's 1 away, right? That's the really broad conceptual understanding of it. If that doesn't make sense to you, don't worry about it that much. This is the kind of thing that will start to become clear as you really understand BFS, as you understand Dijkstra's better, because Dijkstra's is just BFS as well, and that helps with this kind of theory stuff. And also then most importantly, probably when you take a class like 70, you'll learn how to think this way. Anyway, that's why it's true. This is a very hard question. This is like the top end of theoretical stuff we could possibly ask you. Probably wouldn't even ask an exam because look at what I had to do just to convince myself, and you're not expected to be able to do that kind of full train of thought on your own. Anyways, let's continue on. 4. After that one, given a fully connected directed graph, a topological sort can never exist. A few things here about the language. I think the language of this question is not particularly good. Let me erase some of this example up here. First of all, there's no reason to call this a fully connected graph. This just means a connected graph, right? Fully connected and connected mean the same thing, so no need to put that language. Another thing here to note is that this should probably say not just A, but it should probably say at least 1, just to be clear. So in other words, a connected directed graph is a graph in which there exists an edge between every pair of vertices. Not necessarily that there are edges going both ways, but that there's an edge between every pair, at least. So for example, if you had a graph like this, right, and you had something that looked like this is a connected directed graph because, again, there's an edge between every pair of vertices. Okay. Notice that something like this would not meet the criteria because there's no edge between these two vertices, there's no edge between these two vertices, etc. Okay. But also, mainly what I want you to realize is that you don't need the graph to look like this, right? You don't have to be able to go from any edge to any other edge in both directions. That's called a complete graph. That is a different thing than a connected graph. So this, I messed up the first time I did this personally. I was looking at it, I couldn't figure out this problem, and it's because I thought that the graph had to look like this, but that's not the case. The graph could actually look more like this, and it still counts. Anyways, so basically, given a connected directed graph, a topological sort can never exist. Okay, so again, this sounds like a very good candidate to try to prove, because if we can come up with an example, basically, where we show that the statement isn't true, then we've proven it. Okay, again, I'll tell you that this one is basically just false, and let's come up with an example. Okay, so all we need to do, right, is create a connected directed graph where a topological sort can never exist. Here's one. It's just this. This works. If you just have a single node, it's connected, it's directed, and the topological sort is just A. But this is kind of a cheap one, so let's do another one. Here's one too, also kind of cheap, but topological sort in this one is just AB, because basically, right, topological sort is just either the reverse of a post order or just a linearization of the graph. So here's an example of connected, directed, and topological sort exists. But again, this is just kind of a cheap example because it's very small. Let's just say that you want to say, let's say that, given a connected directed graph, with n nodes or n vertices, like, let's just show that this works in general, not just on these really small nitpicky examples. However, you can take advantage of the wording like that. Okay, so for n vertices, how do you do it? Okay, well, so when does a topological sort exist? A topological sort exists when you can linearize a graph. What does that mean? It means that you can basically, if you were to imagine kind of if you were to imagine that you had a graph like this, something like this, and let's imagine that this graph is just beads on a string, right? Like there's a bead A and C and D, and they're all literal like beads or marbles, and they're connected by edges, which are just strings. Basically, if you can hold up the graph from one such edge, in this case A, and have everything draped down so that everything is pointing in one direction, that's a topological sort. That's what it means to linearize something. In other words, you can get all of the arrows of the edges going one way. And you see that all the arrows in the edges are going one way in this example, right? Now, notice that it's still a topologically sorted graph or sortable graph if we make it look like this, right? Notice that this right here that I just drew is the exact same thing as the first graph. I just kind of drew the arrows in different ways because it doesn't matter. But again, you can still imagine if you took A and you held it up like it was a marble, you would imagine that C and D would drop down and B would drop down, right? In other words, you can linearize it. You can turn this into this. My use of an arrow there is a little confusing. You could turn this into this, and you can get all of the arrows pointing one way. What's an example where you can't do that? Generally, an example where you can't do that is when you have a back edge. So you have something like this, right? You have a dependency. So you see if D is pointing back to A, well, now you can imagine there's no way we can get all of the arrows going the same direction, because if we get the C to D arrow going the same direction all the others, well, then the D to A is going to go the opposite direction. And if we get the A to D arrow to go the same direction as everything else, then the C to D arrow is not going to go the same way. So for example, if we took this edge right here and we tried to linearize it, we might end up with something like something like this, which looks good, but then you realize C to D would look like that, so it's not linearizable. This is what it means not to be a topological sort. Another thing is that you could also think of it as having cyclic dependencies, but that's a more technical term, so we're not going to worry about that. Anyways, here's the point. Can you come up with a graph with n vertices, right, that is connected and directed and does not have any of those back cycles? And you probably can. It's actually relatively trivial because all you need to do is have one that goes from vertex 1 to vertex 2 to vertex 3 to vertex 4, ... all the way to vertex n. Great, that's it actually, right? Because this graph, it's clearly linearizable, right? You can clearly get all the arrows pointing the exact same way, right? Because it's just a chain, it's just a linked list basically, and it is connected, right? And it is directed. So this is the part where it's connected, but then we make sure that it's generally connected, but we also want to make sure that there exists a connection between any two vertices, right? Notice right now that there is there's no connection between 1 and 3. So basically the thing we need to do now is say, okay, is there a way we connect 1 and 3 and 1 and 4, et cetera, by adding an arrow that's going in the same direction? And there is. You can just do this, and then, for example, 2 has an edge to 1, it has an edge to 3, but it doesn't have an edge to 4. So you can add one here. You can imagine adding an edge to 5, et cetera, et cetera. So you basically end up with this giant graph that will look like this, where the first node will have a forward edge to every other node, and then the second will have a forward edge to every node that's bigger than it, and the third will have a forward edge to every node that's bigger than it, et cetera, et cetera, et cetera. Right? That means it's all connected. There's a pair of vertices between any two nodes, and we've managed to come up with a graph that's topologically sortable. So this is false because we came up with a counterexample. This is a lot harder of a counterexample to come up with than the tree one, where we're just like, oh yeah, you just do like this and then this and it doesn't work. This this is a very, very complicated type of question. This is very much on the upper end of difficulty that we would possibly talk about. I wouldn't worry about it that much. But if you were curious on how you do it, that's how you do it. Anyways, that is the worksheet for this Tuesday. I hope it helps.